All right, our last section of material in section 1 of our semester. We're going to continue what we did last time, which is more solving equations. So it's almost like these two sections really could be merged together. That just would be a really entirely too long section, so they're separated into two pieces. So first, definition of a solution. A solution is simply a value that makes an equation true. So if you're asked to simply determine if something is or is not a solution, what you're asked to do is to evaluate using that value. So here's an example. I've got an equation, 17 equals 6x minus 1. To decide if it's a solution, that is the number 8 for number 1, is to take that number 8 and to substitute it in for the variable and see if it works. So I have 17 equals 6 times 8 minus 1. What's 6 times 8? And minus 1 is? 47. And what can you tell me about 17 and 47?
It's not the same.
Yeah, they're not the same. It's not equal. And so therefore it is not a solution. Is it a solution? No. So you have to justify that it's not a solution by showing that they don't equal each other. Do the same thing with the second example, 3. Same equation. So 17 equals 6 times 3 minus 1. So what's 6 times 3? 18, and minus 1 is 17. So this time we end up with a solution that works, or with a value that works as a solution. So is it a solution? Yes. So if you're asked to find if something's a solution, you're not asked to solve it. You're not asked to figure out x equals something. You're just asked to take the number and evaluate and see if it works. Make sense? Okay. Now, if you take a look at the next set, you are asked to solve them. They don't give you an x value for you to test and see if it works. You're really solving them from the beginning. So these are going to look a bit like the ones we did last time, but they're going to be more involved. There are going to be more steps to solving them. So if we take a look at number 3, what would we first need to do to isolate the x? Remember, we're undoing processes.
Multiply.
Yeah. So there's 2 steps we'll do eventually. Right now I have the x that has a 23 added to it, and I have a 7 being divided. So I have to both undo the 7 and undo the 23. Remember we talked about how we're working from the outside in, and while we don't see them there, there is an understood grouping of the numerator altogether. So the piece that's the furthest away is the 7, so we're going to eliminate the 7 first. And you're right, we're going to do that by multiplying by 7. So multiplying and divided by 7 will be inverse operations cancel out, leaving me with x plus 23 on the left. And on the right, I get 21. And then what's my next step? Yeah, I'm going to subtract the 23. And if I do that, what is 21 minus 23? Negative 2. And this would be my solution. How could I make sure I'm right?
Plug it into the x.
Yeah, we could do exactly what we did over here, right? We could take the solution we just found, and we can make sure that we didn't make a mistake by taking negative 2 and putting it in for x. What's negative 2 plus 23? 21, and 21 divided by 7 is 3. So it does, in fact, check out. So you could check every single problem, either visually, just making sure sort of mentally does it work, with your calculator, or by hand. Any of those options, you can check all your work. All right, number 4. In number 4, we actually have 2 different components that can be combined. What can be combined right where they are?
3y, negative 8y.
Yeah, these 2 are on the same side. They're like terms because they're both multiplied by y, right? Have y as a component. So we can start by combining those together. So what is 3y and negative 8y?
Negative 5y.
Mm-hmm. And the 9 stays put. So combining pieces, when that happens, within a single side of the equation is a good step. What would we do next?
Make the y, like, isolate the y.
We need to isolate the y. So there's two things that are on the side with the y. There's a -5 and there's a +9. How is -5 combined with the y? It's multiplication. And how is the +9 combined with the y? It's addition. So moving from the outside in, what's the furthest away from the y? Is it the -5 or is it the +9?
What?
I hear mumbling, but nobody. Which of these two pieces is further away or least attached to the y?
Oh, 9.
The 9 is. Okay? So another way I could ask the question is, if you think about our order of operations, please excuse my dear Aunt Sally PEMDAS. We start at the end and we go back towards the beginning when we're working on solving. So the ending part, addition and subtraction, would be what I would be working with first. So it is the 9 that I'm going to be dealing with first. And since it's a +9, I will subtract a 9. So these add to 0. What's -31 and -9?
-40.
-40. Now what would I do to solve for y?
Divide by -5.
Divide by -5. Okay, what's -40 divided by -5?
8.
8. And is it positive or negative?
Positive.
Positive. So negative divided by negative is a positive. And could we check to see that this works?
Yep.
Yeah, we could. I'm not going to check every single one, but I do want you to remind yourself, especially when you're doing the test and you find yourself with 20 minutes left at the end or whatever, that if you wanted to go back and check your work, you have that as an option. Okay, let's try another one. What might you do first on number 5? And you actually have a couple of options that are perfectly acceptable in either direction. So somebody give me an example of something you might do first. Julian.
Subtract -13y from both sides.
Excellent. Okay, we can take -13y off of both sides. So that will make this 0y on the right. So I still have a -7 there. What's on the left?
2y.
A 2y. Anything else on the left?
11.
And there's an 11 at the beginning. So there's an 11 and a +2y. Is that okay with everyone?
Mm-hmm.
What can I do next?
Take away.
Take away what?
11.
The 11. Sure. So we can subtract the 11 from both sides. So the net +11 and the -11 there go away. Leaves me with 2y. And what's on the right-hand side now? Negative what?
4.
Nope.
Or not 4.
18. Yeah. Yeah, they're both negative, so we add them together and we keep the sign. So I now have, just because I'm running out of space, 2y equals -18. Now what?
That makes math.
Divide by 2. And what would we find as our value for y? -9. Okay. Next one's still on this page. So, move that up just a little bit. What might we do first on number 6?
In parentheses.
Yeah, like distribute over the parentheses, right? Yeah, I think that's a good idea. So if we take the 7 and we distribute it across the parentheses, 25 stays on the left. We have 7y, and then what?
35.
Minus 35. And then positive 3y. Okay, now what?
Combine like terms.
Combine like terms. Simon, what terms do you see that are alike?
7y, 3y.
Good. The 7y and the 3y make 10y, yeah? Okay, good.
Minus 35.
Then we can subtract our 35. I agree. Are we going to subtract or are we going to add?
Add.
Yeah, we're going to add. All right. The negative 35 and the positive 35 are on the right-hand side, combining to 0. And then what do I have on the left with the 25 and the 35? Yeah, that's 60. Now what?
Divide by 10.
Sure. Divide by 10. What What will y equal? 6. Okay, are we good? All right, I want to see. Do you guys have some new directions on the next two, or is it just no, you don't. Okay, I need you to write in some directions. There are some directions that are different on the next couple of ones. No, it's not. It's on number 8. Is number 8 on the same side? Okay, is it on the next page? Does it have a new direction set? Oh, good. It's changed in y'all's notes. It's different in mine. Good. Okay. One more problem that's very similar to the ones we've been doing, just more of it. All right, so what would we do first on this one?
Distributive property.
Lots of distributive properties, right? Okay. So I'm going to distribute my negative 5 through and a positive 5 through. All right, so if I distribute my negative 5 through the first parentheses, what am I going to get?
20u minus 25.
Okay, so everybody good with that? All right, and then I have a minus 9u. How about distributing through the second set of parentheses?
5u minus 35.
Yep,
Minus 6.
minus 6. It's looking better already. Now what? Combine like terms. Chloe, what like terms do you see to start with?
20u and 9u, and then 35, or negative 35 and negative 6.
Good. Okay, so on the left-hand side, I have 20u minus 9u, which gives me 11u. And I still have the minus 25 on the left. And on the right-hand side, I still have a 5u, but then I have a negative 35 and negative 6. Negative 41. Okay, we all good with that? Now what?
You could add 41, maybe go across the other side.
Okay. You add the 41. So now I have 11u. What is negative 25 and positive 41?
24.
Close.
Uh, 16.
16. Yeah. You were treating it like the 5 and the 1 were reversed, Simon. Yeah. Okay, 16. And it's positive because the 41 was positive, right? So this is like having 41 minus 25. Over on the right-hand side, these added to 0, so I just have 5u. Now what?
Subtract 11u
Okay.
to both sides.
Subtract 11u. I have 16 still on the left because these added to 0. What's 5u minus 11u? Negative 6u. Now what? Good. Divide by negative 6 on both sides. Now, on the right, that's just u. On the left, these are not going to divide nicely. This is not a friendly number, which is why it's showing up, because I don't want you to think everything ends up being whole numbers or integers. It doesn't. It's negative. Agreed?
Mm-hmm.
Yeah? And the top and the bottom are both even, so I can at least simplify that part of it, right? What is 16 divided by 2? 8. And what is 6 divided by 2? 3. And that's the best we can do in terms of an answer, negative 8 over 3. If it happened to have been, say, negative 8 over 16 or something like that, and your calculator spits back out at you a decimal that's like a nice decimal, you can use it. But this one doesn't. It's repeating. So we're not going to use the repeating decimal form. We'll leave it in fraction form.
So no decimals period.
Decimals are okay if they terminate. Terminate means they stop. For example, if you had gotten something that said 0.16 at the end, cool. But if it says 0.1666666, that's not cool. Yeah. Okay. All right, number 8, the one I was wanting to know if you had different directions on, because I left them off when I did my work originally. Please be careful on the directions in your problems. The directions on all the ones before this said solve. These directions do not say solve. They just say rewrite. So, undoubtedly, there will be a problem like this on your homework or on a quiz or on a test or maybe on all three with these direction sets, and I'm still going to have about 5 of you who are going to solve it for me. And you're going to hate it because it's going to be super ugly and awful because it was never intended for you to solve it. It was intended for a different direction set. So please pay attention to the directions, okay? All these directions say is to rewrite it so there's no fractions. That does not involve solving. What it does involve is looking at the denominators and seeing what number, and there's always more than one option, I could multiply so that I don't have any more denominators. So in particular, what we're really looking for is either a common denominator of 4 and 10, or even better, if you see it, a least common denominator of 4 and 10. Okay? Now, this goes back to what we were doing when we were looking at denominators of fractions. Okay, I'm saying denominator, I mean divisor. It's the same process. So when we're trying to find, if we tried to find a denominator that we could make them both into, like they could be the same, what's an option that 4 and 10 could both be changed into that they're the same? What is it? 20 would be an option. That's actually my least common option. And worst case scenario, truly, if you can't figure it out, you could end up with 40. Either of these are perfectly fine to use, okay? So pick whichever one you'd like. 20 will keep things a little bit smaller. 40 is the easier one to see, just because you multiply the two denominators together. I'm going to use 40, just so that you can see it works, even if I'm sort of doing overkill. It's a little bit too big for what I absolutely need. So what we're going to do is we're going to multiply everything by 40. Okay? So I'm going to write it out. This is 2 times 40 minus 3/4 x times 40 equals 9 over 10 times 40. I'm allowed to do that because I'm doing it to every single piece.
You want us to write it like that?
You don't have to. If you can just show it like that, that's fine. Okay? The reason I'm going to write it out is because it's going to reduce, and it's easier to do the reducing if I've got it written out. So on the first one, it's no big deal, right? 2 times 40 is 80. But on the second one, where I've got the fractions, this 4 and this 40, they will reduce. What's 40 divided by 4? 10. So I end up with the -3 and the x and the 10 all being multiplied. So what is -3x times 10?
-30x.
-30x. On the right-hand side, I have 9/10 times 40. Once again, that 10 that's in the denominator and the 40, this is why I chose 40, right? Or 20. If you want to use 20, it'll work too. The reason I chose this is because it's going to reduce the denominator. I can take 40 and divide it by 10. So what's 40 divided by 10? It's 4. So these cancel and give me 4. So I have the 9 that's still in the numerator times 4, and 9 times 4 is 36. And you stop right there. There's no more denominators. That's what the directions said. If you had chosen to multiply by 20, instead of this answer, your answer would have actually been 10 minus 15x equals 18. Just FYI. It's perfectly fine, right? They're both correct answers. Because it doesn't say how I have to do it, I just need to make sure that the denominators all get eliminated. So this is what happens when you multiply by 20.
And that'd be the LCD.
It would be, yeah. This is the least common denominator here with 20, is 20 of the 10 and the 4, and it would give you this answer instead. Okay, all good? Okay, we're going back to the solving directions. So clearly, the goal of multiplying this to get rid of the denominators is because we want to be able to use that idea to do solving, right? So we are going to now take that idea and use it for these problems where we are going to solve. We're not just eliminating denominators here. Although eliminating denominators is a really good first step. So if you take a look at the denominators of the first one that you're given, number 9, 6 and 8. One option is to simply multiply 6 times 8 and multiply that through all the pieces. That's not my least common denominator. Does anybody know the least common denominator for 6 and 8? It is 24. Okay? If you're not sure how to do that, there's lots of ways. Because the numbers we're working with are typically pretty small, one really nice way to do it is to simply think about your list of multiples. So if I were to list multiples of 8, I'd have 8, 16, 24, 32. I'd have 6, 12, 18, 24. And the first one where they match is the least common denominator. Okay, if the numbers get really big, obviously this is not a great method because you'd be writing out lists for a really long time. But it's not too bad if the numbers are fairly small, and these are. So we're going to use 24 on this one. If you use 48, that's fine. It's not going to hurt anything. So we're going to multiply everything by 24. And just like I did on the last one, I am going to write the multiplication by 24 because it's going to reduce, and I think it's easier to see it do that term by term. If you choose not to, it's okay. Just be really careful as you're doing your simplification that you don't lose something. All right, so they will all divide. I mean, like that's the reason I chose 24 or why you would have chosen 48. What is 24 divided by 8? 3. All right, so this cancels. And I have 3. So I've still got a u, so now it's 3u. How about the next one? I've got division by 6, multiplication by 24. How will these cancel? Yeah, 24 divided by 6 is 4. So now I have a negative u and a 4, so it's negative 4u. And again, have on the other side that 8 and that 24 again. So 24 divides by 8 and gives me 3. 7 times 3 is 21. Now, it may feel like you're doing a lot of work to eliminate the fractions, but here's what you get as the result. Something without fractions. That's a lot easier to solve than adding and subtracting fractions. Chloe, the one that you asked me about in the homework from last time, where we were doing the 1/2 and the 3/4, this would have worked. We could have eliminated the fractions, denominators, and we could have solved it that way too. It would have worked. So what is 3u minus 4u now? Yeah, negative u or negative 1u. We'll write it that way. That's good. Then what would I do? I want u alone. Yeah, divide by what, Hannah? Yeah, divide by negative 1. Or you could even say multiply by negative 1 on this one. What is 21 divided by negative 1? Negative 21. Could you check this in the original problem? Yep. It's not pretty. You might want your calculator to check it for you because you got fractions involved. But you could totally do it, and you can make sure you're right. How about number 10? What denominator could I, or what number could I multiply all the denominators by and eliminate them all? 15. And in fact, 15 on this one is both the least common denominator and the number being multiplied if you multiply them together. So that happens sometimes. Let me shift these over a second. Okay. So yeah, we're going to multiply by 15. So everything by 15. So I've got negative 5/3 x times 15 minus 4/5 times 15 equals 4/5 x times 15 plus 3 times 15. Okay, and remember all those x's are x's. They're not variable. They're not multiplication like symbols. I'm not using x for multiplication because they get intermixed. Okay, so this 3 and this 15, they cancel to what? 5. So now I have negative 5 at the beginning times 5 here, which gives me Negative 25. I'm going to change to red. That blue's not standing out very good. Let's try this.
Wait, where's the x go?
It needs to be there. Thank you for noticing. Yep, negative 25x. Thanks. Now I have the 5 in the denominator of the next piece and the 15. What will these cancel to? 3. Is the red okay to read? It's visible good? Yeah? Okay. All right, so now I have negative 4 times 3. Positive or negative?
Negative.
Negative. Negative 12. On the other side, I have another 5 and 15, making it a 3. So this time I have a 12, but it's 12x and positive. The last one doesn't have any denominators, so I really just multiply 3 times 15, which gives me 45. I almost said it. 45. All right. Now the problem looks like some of the earlier ones we did. What do we do?
Add 12.
Okay, we're going to add 12. We can do that. We have options at this point. We have a couple things we could do. Add 12 is one of them. So if negative 25x equals 12x, these add to 0, plus 57. Now what?
I'll divide by negative 25.
Can't divide by negative 25 just yet.
Subtract all that.
Yeah, we need the x's grouped together, and right now I have an x on each side, so we need to pull them together.
57. Or
Yeah, let's subtract the 12x just because the other x is already on the other side. That gives me negative 37x on the left. These are 0 and 57 on the right. Now what? There's my division. Divide by negative 37. And our answer is super ugly. You can put the negative in front, and that's about it if you want in terms of like writing it differently. 57 and 37 are actually both prime. They don't divide by each other or anything. Like nothing simplifies out. It's just ugly. I take it back. 57's not. 37's prime. 57 actually divides by 3, but 37's prime. Okay? So is it okay to have an answer that's ugly? Yeah, it is. It's okay to have an answer that's ugly. Doesn't mean you have to like it. Any questions on either of those two? These are the messiest ones by far that we've done. Okay, number 11. The last messy one. The other two problems after this are cleaner. So process is the same. What do I need to multiply by to eliminate all denominators? 4. You're right, Julian. So the least common denominator for this would be 4. If you wanted to multiply by 8, you could. I'm going to actually write it as is, just times 4, because it's got enough space here on this one to do this. On the left, 4 times negative 3. Negative 12. On the right, even though the numerator has like more things going on in it, it doesn't matter. The 4 is being multiplied by something that's being divided by 4. So these still eliminate each other. You don't distribute the 4 through the top. None of that happens because the entire numerator is both divided by 4 and multiplied by 4. Those operations cancel. So the numerator doesn't end up actually being multiplied by anything, or if you wish, you could say it ends up being multiplied by 1. However, the negative that's in front like that means it applies to everything in the numerator. So the negative applies to the 3x, but it also applies to the positive 3. So I get negative 3x minus 3. And again, what's happening is that this negative is applying to each piece of the numerator. Okay, how do I know? Because it's in front of the entire fraction. If it were up with the negative, like the 3x right beside the 3, it wouldn't. But it's in front of the entire fraction. This negative will do the same thing. It'll apply to everything inside. But on this one, when I take a look at the 4 and the 2, they don't completely go away like the 4 and the 4 did, right? So when I cancel this 2 and this 4 out, what happens? What is 4 divided by 2? It's 2. I have a 2 left. So there's a negative that's distributing through, and there's a 2 that's distributing through. Both of them. If it helps you to think of it, you're doing it like this. There's a negative and a 2 that are going through. So negative 2 times 2x is negative 4x, and then negative 2 times 3 is negative 6. Okay, somebody tell me what we can combine.
Like terms.
Like terms. Can you give me an example, Simon?
Negative 3x and negative 4x.
Awesome. These two are like terms. They make negative 7x. What else can I combine?
The 3 and the 6, both negative.
Yep, the negative 3 and the negative 6, which will give me
Negative 9.
negative 9. Okay, those are all the like terms for where they're currently located. And then what?
When you have a thing that says negative 12 equals negative 7x and negative 9, can you just swap all the numbers at that point?
Do you mean can you make them all positive?
Yes.
You could.
All the signs, not
Mhm.
numbers.
Yeah, so because they're all negative, that seems a little bit unnecessary, and you're right. The equivalent to what you're asking is, could I just divide everything by negative 1 or multiply by a negative 1? And you certainly could. If you'd like to do that, we can change all of our signs right now. If you don't do that now, you'll eventually do something equivalent later, so it doesn't matter when you do it. What could we do next?
Minus 9.
We can subtract 9. So what's 12 minus 9? 3. So now I have 3 equals 7x, and
Divide by 7.
divide by 7. Yeah. So it's not a very nice number again, right? In this instance, it's not a whole number or an integer. It's fraction 3/7. Okay, you ready for doing the last two that are cleaner, a little easier to work with? Okay, the directions change again. This one actually talks about the number of solutions that equations can have. All the ones that we've done so far, every single problem, the first 10 examples, all had, well, actually the first one did too. I didn't have 10 examples, but I had 8 examples in between there. Problems 1 and 2 were a little different. They'll have one solution. Every single one of them had one solution. That's not the only way a problem can show up. Some problems have 0 or infinitely many solutions. So you've already seen many examples today of problems that have one solution. How do we know? Well, because at the end you got x equals and it was one number, or you got y equals and it was one number. That's how you know. So when we are trying to decide how many solutions something has, the process is just like we're doing on the previous problems. We're attempting to solve it, and we're going to see what happens. So looking at this one, I have 4 times x plus 2 equals 4x plus 6. So what would we do first? Distribute. We can do that. So we'll distribute through here. So I have 4x, what?
4x.
Plus 8. What might you do next?
Combine like terms.
Combine like terms. Which terms would you like to combine?
4x plus 4x.
Okay.
4x minus 4x.
All right. So I could subtract 4x to shift the 4x's and combine them. That cancels this out. It cancels this out. And now I have 8 equals 6. It's a problem, right? I mean, at least it's not true. 8 does not equal 6. Yeah? So what happens when I get something like this, where the end result is a statement that's flat out false? Well, it means that there's no solution. So if you get to this point and you have a false statement, there is no solution. If it asked you how many solutions are there, you would say 0. There's no solution. And if you look back at the previous line before we subtracted the 4x, it kind of makes sense. The 4x's match, right? But one of them has 8 added to it and one of them has 6 added to it. Well, I can't have two things that match and add 8 to one place and add 6 to the other place and get anything that works. That's not going to work. Okay, let's try the next one. We will distribute just like we did in the previous one, right? So our 2 will go through here. So I have 8x plus 3. Anything I can do on the left-hand side, excuse me, to simplify?
Wouldn't it be plus 6?
Or did I write something wrong? Oh, I did. Thank you. 8x plus 6, thanks. Anything on, yeah, I can. What like terms do you see?
The x's, 5x and 3x.
Yeah, the 3x and the 5x, which gives me
8x
8x
plus 6.
plus 6. Okay, pause for a moment. What do you notice?
They're
They're
the same.
the same. And if you don't notice it now and you start trying to do what we did a minute ago, like with the minus 8x's, which would be okay, right? If you didn't notice it right away, you end up getting this one where 6 equals 6. And the statement is different than the last time, right? Last time when I got to here, I had a statement that was false. This time when I get to this point, I have a statement that's true. And you don't have to stop there. You could stop here and it'd be okay. At either place, hopefully you're looking at it now and you're noticing it's exactly the same on the left as it is on the right. What does it mean? It means any value for x will work, right? Think about it from the 8x plus 6 example. If x is 1 on both sides, are they going to be the same? Yeah. If x is 10 on both sides, are they the same? Yeah.
So it's infinite.
Anything. So it's infinitely many solutions. Yep. So either of these points at this point tell us that we have infinitely many solutions.